Hello and welcome to a new chapter on oscillations, and in this lesson we will nail two important ideas. One, what is simple harmonic motion, and two, how this motion can be represented by a sine or cosine function. So before I start, let me say this topic is a little complicated. So do not get disheartened if you're not able to understand it first time around. Focus on the definitions and the link that connects graph to the equation. So what we have here is a particle that is oscillating about the origin on the x-axis. And you can see it is moving left and right by the same distance. So here one oscillation or cycle is out and back to the same state, like this or this. That is, particle comes back to the starting position and starting velocity. Then we can say that the frequency f of the oscillation is the number of times it completes a full oscillation in 1 second. So if this oscillates 3 times in a single second, we say its frequency is 3 cycles per second, or simply 3 Hertz. Then we can also say that time taken for a single oscillation is 1 upon f, which is simple math. That is, if f oscillations happen in 1 second, 1 oscillation happens in 1 upon f seconds. And we term this time for one cycle as a time period t of the oscillation. Now we have a simple definition for periodic motion, that is, any motion that repeats at regular intervals is periodic motion. Now, in this lesson, we would want to focus on a particular type of periodic motion that is called simple harmonic motion, where the condition is that the restoring force, or the force that tends to bring back the mass to its equilibrium position, is proportional to displacement. And this type of periodic motion follows a sinusoidal function of time, which in simple terms means that it can be written as a sine or a cosine of time t. And let us see what each term means here. So A is the amplitude or maximum absolute value of x. So A is always positive. Omega is angular frequency in radians per second, and phi is a phase angle in radians that tells us the position and direction of the particle's motion at time t equal to 0. And we will explore each term a lot deeper to get complete clarity as we move ahead. So let us say a mass starts from extreme right. So here at t equal to 0, let us say x is equal to 6 meters. Then this magnitude of displacement from the mean position is what we call the amplitude A, and this can be measured on either sides. Now it is released to oscillate. So we see that here it just completed the first oscillation and now the second oscillation. And you can see it took 4 seconds to complete one oscillation, which means its time period is 4 seconds. And therefore, its frequency is 1 upon t, or 1 by 4, or 0.25. That is, in 1 second, it could complete only 1/4 of an oscillation. Well, a fast one like this is doing 5 oscillations in a second, and that is its frequency. Okay, now let us focus on one single oscillation and try to plot the position of this mass with respect to time. And for this, we will take time on y-axis and position on the x-axis. Now, this might sound a little unconventional, that is, putting time on y-axis, but you will soon see that this will provide a better visualization and understanding of the topic. And we will move the mass in steps rather than one single smooth motion to understand it better. So we can see at t equal to 0, the mass is at 6 meters. Then a little while later, it is here, and you can see its corresponding position on this graph is here. By t equal to 1 second, it is at x equal to 0 meter, and by t equal to 2 seconds, it is at minus 6 meters. That means it has completed half the cycle, and then it starts its return journey. And we see at t equal to 3 seconds, it is at 0 meter or back at the equilibrium position. And at t equal to 4 seconds, it is at x equal to plus 6 meters, again completing one full oscillation. And so you get a graph like this. Now, if we make the same graph with a small change, and that is we invert this graph by taking time on x-axis and position on y-axis, let us see how it looks like. So once again, we move in steps, and what we get is this. And if we continue plotting for more such cycles, the graph continues as a repeating wave called the sinusoidal wave. So if the relationship between displacement and time is a sinusoidal wave like this, it represents simple harmonic motion. Conversely, if the motion is simple harmonic with no energy losses or damping, the displacement time graph will always be a sine or a cosine wave. And you see here, each complete wave section is one cycle. So here at end of 4 seconds, one cycle is completed. At the end of 8 seconds, 2 cycles are completed. And at the end of 12 seconds, 3 cycles have been completed, and so on. Okay, now having understood the concept of what a sinusoidal wave is, would it not be easier to represent this graph and therefore the simple harmonic motion of this mass at any time with a single equation rather than dealing graphically, which actually does not seem very convenient? So the answer is yes. And here for this case, we find that equation is x is equal to a cos 2 pi t upon capital T. This means that if you know the amplitude a and time period t, you can substitute any value of time to get corresponding displacement or position x. So here a is equal to 6 meters, t is equal to 4 seconds. So this wave can be written as x is equal to 6 cos 2 pi t upon 4. And we can also do a check whether this equation gives the right output or not. So let us try t is equal to 0 seconds, and what we get is x is equal to 6 cos 0, which equals 6 meter, and that we can see is correct. Let us now try t equal to 1 seconds, for which we get x is equal to 6 cos pi by 2, which equals 0 meter, and that is correct again. Then at t equal to 4 seconds, x is equal to 6 cos 2 pi, which equals 6 meter, and that is correct again. And if we go further down, say t equal to 22 seconds, x equals 6 cos 11 pi, which equals minus 6 meter, that is also correct. So we see this equation correctly describes the motion of this particle. Also notice the term small t by capital T that basically tells us what fraction of a cycle has passed. And when we multiply that fraction by 2 pi radians, or the angle for one full cycle, we get the total phase in radians covered. Now you could say that this equation seems to fit in well as long as you start the motion from extreme right, that is this position. But what if the block starts from the middle, that is at t equal to 0, x is equal to 0 meters, and it is moving left? So let's check if the same equation works. At t equal to 0, x is equal to 6 cos 0, which is equal to 6 meters, which is clearly not correct. That is, it should have been 0. So what we do is modify the equation to x is equal to 6 cos 2 pi t upon 4 plus pi by 2 and see if this works. So at t equal to 0, in this equation, x equals 6 cos pi by 2, which equals 0 meter. That is correct. And if you try other values of t, you will find that they would also give the correct results. So say at t equal to 3 seconds, we get x is equal to 6 meters, which is true again. So you see, this equation now fits a situation where the motion starts from the position x is equal to 0. But what you must further notice, and this is very important, is that when the mass is at x equal to 0, at t equal to 0, it could have moved either way, that is right or left. And here it moved left. So adding pi by 2 gives you an equation where the particle moves to the left at first. However, if you had put minus pi by 2 here, the particle would have moved to the right first, that is at t equal to 0 seconds. So you see, the sign of phi sets initial direction of motion. Okay, now what if the box starts from extreme left, that is at t equal to 0, x is equal to minus 6 meters. Well, you can modify the equation as x is equal to 6 cos 2 pi t upon 4 plus pi. And you'll find the x values for various time values would be correct for this equation if it starts from extreme left, that is the box starts from extreme left. So we can say that the general form of equation for displacement of a particle undergoing simple harmonic motion is x is equal to a cos 2 pi small t upon capital T plus phi, where a sets the vertical scale and the sole purpose of phi is to describe the motion of the particle accurately with reference to where it starts when we set the time t equal to 0. So depending on the starting position, phi will need to be appropriately changed. Okay, now we also know that 2 pi upon capital T is equal to omega, or the angular frequency. And here it represents a rate of change of an angular quantity that is not necessarily related to a rotational motion. And we will cover this in a more detailed way in a subsequent lesson. Then we can rewrite this equation as x is equal to a cos omega t plus phi. So now, to get a better sense of what this equation really conveys, let us compare three different waves against a blue wave that has an amplitude of 10 meters, time period of 4 seconds, and phase angle of 0 radians, which means the particle starts at x equal to x max equal to 10 meters. So we will keep the blue wave constant for comparison. Okay, here in this one, we see both the waves have the same time period but different amplitudes. And of course, same time period also means the same frequency. Here in the next one, we see the simple harmonic motion have the same amplitude but different time periods. And here in the third set, we find both the waves have the same amplitude and time period but a different phase angle, which essentially means the particle that corresponds to the red wave starts at a different initial state. So you see, this equation allows us to find the displacement at any instant for an oscillating mass in simple harmonic motion, and understanding the physical meaning of each term, that is amplitude A, angular frequency omega, and phase angle phi, is very important. And let me say again, if parts of this lesson felt tricky, that's normal. Watch the lesson again and review your textbook. It'll help you solidify how displacement and time are connected in simple harmonic motion and how this relationship forms a sine or a cosine wave.